Okay, the last section of Chapter 11 covers how we go about determining the pressure, volume, temperature relationships for gas mixtures. And so we've focused pretty much everything so far on just looking at a pure substance. But then the question is, when we have a mixture of pure substances, how do we go about determining the various pressure, volume, temperature relations, as well as enthalpy, internal energy, and entropy? How do we determine the value for the ensemble of multiple pure substances together? And so when we do have a system involving a mixture of two or more components, how do we determine those properties? Well, one of the things that I'm sure you remember from your chemistry class is that we can define a mixture by how much of each of the species, each of the components we have in that mixture. And we remember from chemistry class that the mole was a measure of the number of individual molecules or atoms associated with a particular species or component. And that if we assume that we have J different components, we could then add up the total number of moles associated with the mixture, call that capital N, and then we can define a mole fraction. And the mole fraction is just the ratio of the individual amount of moles divided by the total number of moles. And so Y sub I will be referred to as the mole fraction. Now, we don't want to confuse this with the mass or the the mass or the volume fraction associated with a two-phase mixture that we saw before when we were under the dome. But in this case, our mole fraction will be given by Y sub I. And we recognize that if we added up all the mole fractions of a mixture, that would have to then equal to 100% or 1. And so when we now have, for instance, if each of the components was assumed to have an equation of state, and let's say the equation of state was a two-parameter equation of state such as we had with the van der Waals equation. Well, in that particular case, each of the individual components would have a corresponding A and B parameter. And so one way of bringing together the equations of state for each of the components is to bring them together and weight them in a certain fashion, and in this case, weight them by the corresponding mole fraction in some type of a summation type of process. And so in essence, that's what's shown here. You know, we could have, for each of our components of a gas mixture, we could have an A sub I, and we could then come up with a total. Likewise, when we talk about a critical temperature and a critical pressure, each of the individual components would have a critical temperature and a critical pressure, and we could weight those individual critical temperatures and critical pressures by the mole fraction, sum that all up, and get then a corresponding critical pressure, a weighted average corresponding critical pressure and temperature. And so this would come into play. Let's say that we were dealing with something like air, which we know is made up of nitrogen and oxygen. Nitrogen and oxygen both in cryogenic conditions have a dome, and they have a critical pressure and a critical temperature. And if we said that we had a mole fraction of nitrogen that was 0.79 or 79% by volume, and oxygen was 21% by volume, we could determine what would be an appropriate critical temperature and critical pressure associated with air as a mixture of gases. We also know from various chemistry equations that as we bring together a mixture, and we'll talk a little bit more about this next time in the next chapter, but we know that each of the individual components of a mixture at a given temperature for a given volume, if we were to put each of the individual components into a constant volume at a given temperature, the overall pressure after we mixed them all together would be a sum of each of the individual what are referred to as partial pressures. And so we will have that relationship that we'll talk about, and this partial pressure would be what would be the pressure that a particular mixture of gases would occupy if they were in the overall volume at some mixture temperature. And we see here that we could introduce the compressibility factor and the number of moles of that particular component. And in doing that, we would see that this additive pressure rule would basically tell us that the mixture would have a compressibility factor that would be directly related to the compressibility factor associated with each of the individual components. At again that temperature and volume, which would correspond to a given additive pressure, partial pressure. And then we also can think of bringing mixtures of gases together, and if we brought them all together and each of them had the same pressure as the final pressure, but at the same temperature, each of the gases would have a volume that corresponds to that particular amount of gas mixture component, and those volumes would all add up to be the final volume. And under that particular case, once again, the individual volume would correspond to a gas that was at the mixture pressure and the mixture temperature with the number of moles and its corresponding compressibility factor. And we would have again a similar expression for the overall compressibility factor for the mixture if we were able to again determine the compressibility factor for each of the components at the pressure and temperature of the final mixture. When it comes then to determining the other thermodynamic properties, we basically say that each property associated with the thermodynamics of the pure substance for a mixture, each property would have a value, a generic value, let's call it X. And what we can think of is that we could then define a partial molar property, again, for a mixture. And if we then said that this X bar for each component was how does that particular property change with a change in the number of moles of that particular component at the temperature, at the pressure, holding all of the components constant. Okay, we can define this partial molar property. The final property then would be a weighted average or summation of that molar property. So with that in mind, suffice it to say then that the total volume, the total internal energy, the total enthalpy, and the entropy would just be directly related to the individual partial molar property, whether it's volume, internal energy, enthalpy, or entropy, weighted by the number of moles of that particular component, summed up for all the components, such that we would then have a mixture property associated with that particular ensemble of different number of moles of different species. We will also, in the chapter on combustion, we will introduce and talk a little bit more about the Gibbs function that we defined briefly a couple of lectures ago. Also, another free energy term, this phi. Again, we'll define that in combustion, but in essence, we can talk about something that is referred to as a chemical potential. And that chemical potential is related to how this Gibbs function changes for a particular component in the mixture if that component changed, holding everything else the same. So one can think of it as, let's say that we had a mixture of oxygen and nitrogen, and the oxygen was 21%, and the nitrogen was at 79%. Okay, that mixture of nitrogen and oxygen would have a certain Gibbs function associated with it. Now, if we looked at just the oxygen and allowed the oxygen just to change slightly in how many moles, holding the number of moles of the nitrogen constant at the temperature and pressure of the mixture, and then obtain or determine how the Gibbs function, that thermodynamic property called the Gibbs function, changes with a small change in the number of moles of the one component, that would be the chemical potential for that particular component. And so we could have that for each of the individual components, and the total Gibbs value then would be related to a weighted chemical potential for each of the individual components. And so these equations here we'll see a little bit later as we discuss the concept of equilibrium in a combustion reacting system. There's another parameter called the fugacity, and the fugacity has units that are similar or the same as pressure units, and basically the fugacity is just a term that allows us to observe the performance of a substance as the pressure departs from low values. And so we will talk about that. Again, it's a property that is used in multi-component systems. Those types of systems are typically involved when we have reacting type of equilibrium combustion systems, where we have multiple components that show up and they have an effect on the properties associated with the substance. And so that then finishes this particular chapter. We started off by discussing the equations of states involving possibly a compressibility factor. And we saw that there were different types of equations of states. Some were two-parameter equations of states. We then looked at the effect of assuming a thermodynamic property could be written as an exact differential, and that allowed us to obtain a series of relationships with respect to those variables, and that then allowed us to determine all of the Maxwell relationships, and showing the interaction between all of the defined type of properties such as enthalpy, internal energy, entropy, and how they're related to the measured properties such as temperature, pressure, and volume, as well as mass. And so with that, we had all of those property relationships in table 11.1. There's too many to show here, but you can refer to the table in that particular case. And then we also introduced for phase change the Clapeyron equation, and then we also looked at how to obtain changes in entropy, internal energy, and enthalpy utilizing mixture type of data, or measured data such as temperature, pressure, volume, and C sub P relationships. And then we finished off the chapter discussing the concept of a real gas behavior. One of the options that we have when we are studying gases, we can either assume it's a perfect gas, an ideal gas, or now we have the capability of having a real gas behavior. As we get closer to the dome, we want to make sure we have the thermodynamic properties as close to reality as possible. And then we had some other thermodynamic relationships or functions that were introduced, various other parameters like the speed of sound, the expansivity, the Joule-Thomson coefficient, and then we started to discuss the concepts of multi-component mixtures that will be highlighted in the next chapter and then acted upon in the chapter on combustion. And so these, again, some of the relationships based on mixtures of gases and some of the thermodynamic properties that we use in order to look at the behavior of gases and compare those behaviors to ideal gas behaviors. And that ends up this particular chapter.